Welcome to QSTI Prep Academy. I am so pumped you're joining us today. We're tackling a pretty massive topic for your certification. It's EPA Method 2H. You know, if you've ever dealt with stack gas velocity, you already know things get, well, a little weird near the stack walls. And that is exactly what Method 2H is all about. We're going to master that velocity decay near the stack wall. So let's dive right in and get that overall important view of how this methodology fits perfectly into your field testing.
Okay, here's our game plan for today's explainer. Number 1, the wall effect problem. 2, default adjustment factors. 3, a quick midpoint review. 4, traverse point locations. And 5, calculating the final velocity.
All right, kicking things off with Section 1, the wall effect problem, specifically frictional decay. So picture this physical reality for a second. Gas is flowing through a massive stack, right? But it actually slows down when it scrapes against the walls, just because of friction. That creates what we call our wall effects, unadjusted average velocity. Honestly, by itself, this average stack gas velocity is just incomplete because it totally ignores that decay. Method 2H is going to take this unadjusted number, and when you pair it with methods 2, 2F, and 2G, it transforms it into a highly accurate adjusted figure.
Now, you might be wondering, how exactly do we fix this unadjusted velocity? Well, you've basically got two options. First up is the calculational approach. This means doing the rigorous field math. You're actually deriving a factor from real velocity measurements at 16 or more points. Your second option is the default procedure. This is basically your regulatory shortcut, assigning a generic adjustment factor based purely on how the stack is constructed.
Moving right along to Section 2, default adjustment factors. Let's talk about that shortcut.
This right here is the ultimate shortcut, and it's absolutely going to be your easiest solution on the QSTI exam. If you want to skip all those extra field measurements, you just use pre-approved wall effects adjustment factors, or WEFs. Seriously, burn this number into your brain right now, 0.9900. If you're dealing specifically with a brick and mortar stack, the EPA says, hey, go ahead and multiply your unadjusted velocity by exactly 0.9900.
But what if it's not brick and mortar? Well, for literally all other types of stacks and ducts, the default WAF is 0.9950. You can apply this directly to your unadjusted velocity. It's that simple. Brick and mortar is 0.9900, everything else is 0.9950. Guys, these are incredibly easy automatic points on the exam.
All right, Section 3, the midpoint review. Time for a little halftime check-in.
So, we know friction slows the gas down, and we know default factors can fix it pretty fast. But hey, before we dive into the really heavy equations of that calculational approach, make sure you hit subscribe. And if you really want to pass that QST exam, send an email right now to qstprepacademy@gmail.com. Just write us there, we're here to help you succeed. Okay, so we've mastered the defaults, right? Let's get ready for the field math.
Which brings us to Section 4, traverse point locations. Let's get into the field math.
Okay, so if you aren't using those default factors, you absolutely must use the calculational approach, utilizing some really precise field measurements. Out in the field, you've got two main choices. Step 1 could be a partial traverse. This requires a minimum of 2 points per sector closest to the wall. Specifically, you're looking at 1 inch from the wall and then a calculated point we call DREM. Or Step 2, you do a complete traverse. This means you're taking measurements at 1-inch intervals all the way up to 12 inches from the wall, plus your DREM point.
All right, let's write this out on the board. We're looking at equation 2H2 up there. This formula calculates DREM. That's the distance from the wall to the centroid of the remaining area, right between your last 1-inch measurement and the interior edge of your equal area sector. I know, it looks super intimidating, but honestly, you're really just plugging in your radius, R, and your D last.
Next up, let's sketch out equation 2H-4. This one is all about calculating D-B, which is the interior boundary of your equal area sector. Now pay attention because here is a vital rule for your test. Your last 1-inch measurement, your D last, absolutely cannot be closer to the center of the stack than this interior edge, DB. You're going to use this exact formula so you know exactly where your wall sector ends.
All right, Section 5, calculating the final velocity. Let's bring it all together.
This is the final math stretch, folks. We are bringing everything together to find your final, beautifully adjusted velocity. Let's establish our baseline by writing down equation 2H-5. First things first, you need to find the unadjusted average velocity, VAV. It's straightforward. You just sum up your interior velocities, add your exterior sector velocities, and divide by the total number of points, N. This gives you your baseline before we do any of that method 2H magic.
Now watch how this changes as we write out equation 2h minus 17. Look at that. This is your wall effects adjusted average velocity. Do you notice the difference? We take the exact same structural framework, but we replace those original exterior velocities with our newly calculated replacement velocities. That's that VEJ with the little hat on top of it. By doing that, you've successfully factored in the friction.
And here is the grand finale equation we're writing up, equation 2H19. To find your calculated wall effects adjustment factor, your actual WAF, you just take that brand new adjusted velocity we just found and divide it by the original unadjusted velocity. Boom. Done. You have officially derived your own highly accurate adjustment factor straight from your field data.
But hold on just a second, because there are rules. Let me point right up here to table 2H2. Even if you calculate your own WAF beautifully, the EPA sets some very strict minimums. Check this out. If you did a partial traverse, your calculated WAF cannot be reported as lower than 0.9800. And if you did a complete traverse, it can't be lower than 0.9700. Bottom line, if your math gives you something lower than those thresholds, you have to discard it and default to these exact minimums.
Wow, okay, we've covered a ton of ground today in this explainer. So I want to leave you with this somewhat provocative thought. How does method 2H change the way you'll approach methods 2F or 2G in a real-world stack test? Think about it for a minute. These adjustment factors directly impact the total volumetric flow rates you're reporting with your 2D and 3D probes. It quite literally changes everything about your final numbers. Let that sink in, keep studying hard, and I will see you in the next QSTI module.